Hello, this is the first of a two-part video that put together to try to motivate you why you might want to study the p-adic norms. So this first video, we're going to derive a old formula for the sums of powers of integers. So we'll write down real quick. So 1 plus 2 plus n minus 1 to the k is equal to the sum from j equals 0 to k of k choose j, b sub j, and then n to the k minus j plus 1 over k minus j plus 1. So the main thing we're going to do in this video is come for this formula. You might ask, what does this have to do with p-adics? By itself, nothing, but it's going to be the starting place for the video that does. And let me tell you just real quick where that's going to go. So you notice this right-hand side here is a polynomial in n. So we could just give it a name, say sk of n. Well, if I look at the very last term of this series where j equals k, so this binomial coefficient is 1, I have b sub k, I have n to the 1 over 1. So if I just think about this polynomial here, I have sk of x, the lowest power of x in it is b sub k x, and then we have order x squared things. Well, if I wanted to know about these numbers, these b's, which these are the Bernoulli numbers, by the way, we'll talk about them here in just a minute. You notice I could compute the Bernoulli number by taking this polynomial, dividing it by x, and then plugging in x equals 0, right? Well, I don't really know about anything about this polynomial divided by x. And certainly, well, the next idea you would probably have if you've taken calculus is say, well, let's try doing b sub k is the limit as x goes to 0 of sk x over x. It's a great idea. The problem with it is the only values where I know anything about what this guy is going to be equal to is for the positive integers, right? So I know something about sk of n for n and z, or n and n, but I don't know anything for other values of x. And so I'm stymied on wanting to take this limit because I don't know anything about the value of this polynomial for small values of x. But that's where the p-adic norm is going to come in. So it turns out, I mean, we'll talk about the p-adic norm in the next video. But if I look at the p-adic norm, then the sequence p squared, p cubed, p to the fourth. So p is a prime number, by the way. This sequence converges to 0 in the p-adic norm. And so even though I don't know anything about this for small real numbers, I do know something about it for small p-adic numbers, so small elements in the p-adic integers. And so I can take this limit as my elements go to 0 and find out something about bk. What I'll actually find out is I'll find out what the denominator of bk is. So, or even more than that, I'll find out what is the value of bk up to an integer. So the fractional part of bk can be computed this way. So that's what we'll do in the next video. But since this first formula that we're starting with isn't terribly common anymore, I thought I would take one video just to derive this formula real quick, and then we'll use the other video to get this results about the Bernoulli numbers. All right, well, let's get started. So let's say we want to compute this sum, 0 to the k, 1 to the k, n minus 1 to the k. Why stop at n minus 1? Well, just it winds up the formula. It's easier that way. So when you have a sequence and you want to study it for a whole bunch of values at once, a good idea is to make a generating function. And there's lots of options for this. You could do something like some sk of n. I could do two variables, put x to the k, y to the n. Or I could just pick a value of n and do one variable. So just do SK, or I could just sum on n. So there's lots of options there as far as which ones I decide to sum over. And then I also have the issue, well, what do I tack onto this? So I could put x to the k would be the easiest, or the next easiest choice is x to the k over k factorial. So if it's just x to the k, that's called the arithmetic generating function. If I do x to the k over k factorial, that's the exponential generating function. I can also do things like e to the kx and get some sort of Fourier series. But in practice, you just try different ones and see which one works. Turns out for this one, this exponential generating function is going to come out really nicely. So let's compute it real quick. If we go k equals 0 infinity, what is sk of n? Well, sk is sum from j equals 0 to n minus 1 of j to the k. And then we have x to the k over k factorial. Okay. This is a finite sum of absolutely convergent series, so there's no problem changing the order of summation and summing on k first. So if I sum this guy on k, I recognize that as being, that's the Taylor series for e to the x, right? This is sum from j equals 0 to n minus 1. This is jx to the k over k factorial. So this is e, it's the jx. Right? And then this one is 1 e to the x, e to the 2x, e to the 3x. That's a geometric series. So I also know the sum of it. It's e to the n x minus 1 over e to the x minus 1. Okay. All right. So we got a closed form for this exponential generating function. Now the idea is if we want to know what these coefficients are, which is the sum we really cared about, we try to compute the Taylor series in a different way, and then we can compare the coefficients. So this thing is a pretty simple formula. So we're going to be able to compute it just basically factoring it. So if we rewrite this, e to the n minus nx minus 1 over x, and then x, e to the x minus 1. There's a good reason for doing this. One is this first piece is really simple. It's just an exponential series. I mean, we take away the constant term and knock down all the powers, but we can find that series very easily. The second series, it's hard to say what it is, but notice it doesn't depend on n anymore. So Bernoulli's idea was, well, let's just, by definition, say this is, okay, I've already used k and j. Well, I think I can use j again. It's not going to hurt. So let's just say this is bj, and then x is j over j factorial. And then these have become known because of this idea, the Bernoulli numbers. All right, so this is one specific holomorphic function at 0. I mean, you see there's a removable singularity at 0. So if we knew its Taylor series, that's what we're going to define to be the Bernoulli numbers. And then the dependence on n is very simple because, well, let's just write out. E to the nx is 1 plus nx squared over 2, so on and so forth. Then I subtract the 1 and divide by x. So the 1's cancel. So I've got at least an x in each one of these. I've also got an n in each one of these. So I can write that as being n. And then what's left is 1 plus nx over 2 factorial, nx squared over 3 factorial, and so forth, cubed over 4 factorial. So we see that this first part, now I do need another variable. Let's call it r. R is 0 to infinity. So there's an n on the whole thing. And then there's nx to the r over r plus 1 factorial. All right. So here's our first series. There's our second series. We multiply them together and we should get the generating function we started with. So I'm just going to scroll and then rewrite that. So if I go sum from k equals 0 to infinity sk of n x to the k over k factorial. This is, well, first we got the Bernoulli part. Sum from j equals 0 x to the j over j factorial. And then times n, sum from r equals 0 infinity nx to the r over r plus 1 factorial. All right. So how do we extract from that just a formula for Sn? Well, it's just multiplying two series. If I want the coefficient, the kth coefficient in the product, what I should do is take the jth one in the first, and then the k minus jth one in the second, and then sum that over j. So the kth coefficient here, of course, is skn over k factorial. That's going to be, I'm going to sum over j, take the jth coefficient here, so bj over j factorial, and then the k minus jth here. So I've got my n, and then I've got n to the k minus j over k minus j plus 1 factorial. And the sum, the last term that will make sense is when j equals k. Okay, well, we're nearly there. So if we move the k factorial to the other side and do just a little bit of rearranging, so skn is sum from j equals 0 to k. I've got my b sub j guy here. If I move the k factorial, I'll have k factorial on top, j factorial on bottom. From this k minus j plus 1 factorial, I can take just the k minus j. So we've got k minus j factorial. Did that because now this is the binomial coefficient. And then what's left, we have n to the k plus 1 minus j. And what's left in this factorial that we didn't take, well, it's just that very last term. So k plus 1 minus j. And that's it. Because again, this is just the binomial coefficient. And so we get this formula that we wanted at the beginning of the video. This is k choose j, b sub j, and then n, oops, it's k plus 1 minus j over k plus 1 minus j. All right. And then like we said, why is this important is because this shows, I mean, what we're going to do in the next video is we're going to use this as our getting off point, because it says that in particular, b sub k should be the limit as x goes to 0 of skx over x, or if we work in the p-adic norm, that's the same as saying the limit n goes to infinity of sk p to the n over p to the n in the p-adic norm. All right. So in the next video, I'll actually do the arithmetic and try to evaluate this limit, and we'll see how that gives us the value of the Bernoulli numbers up to an integer. Thanks for watching.